valid for orthogonal coordinate systems, so Cartesian, spherical. Do you have a question? No. Thanks, Art. Okay. I'll add you to the list of people who correct me now. All right, so so this equation is valid for Cartesian, cylindrical, spherical coordinates, any orthonormal coordinate system. So in the homework, I'm going to ask you to express this equation, to rip it apart and express each component for cylindrical coordinates. But you're going to run into trouble essentially with this term. Okay, so I'm going to show you how to expand this term even for the Cartesian case. Okay, when we wrote this equation for the conservation form, it was kind of easy the way you do it. We said, okay, what are you transporting, rho u or rho v, right? And rho w, you replace that and you do the divergence. That was easy. Over here, it's not very clear. Which u do you set? Which u are you transporting? Is it this u or this u? So there's another way to deal with this term. And you simply do u dot grad u. And I'm going to do it in Cartesian, okay? So this is u v w, right? You just write it out. Grad u, you just write it out as du vector by dx and du vector by dy and du vector by dz. You agree that this is correct? Okay. Now simply take the dot product. You get u scalar du vector by dx plus v scalar du vector by dy plus w scalar du vector by dz. Okay, now how do you deal with du vector by dx? You just simply differentiate. So du vector by dx is really d by dx of the u vector, which is ui plus vj plus wk. Now this is going to be important because each one of those terms, so d by dx is a linear operation, so the derivative of the sum is the sum of derivatives. Agreed? So this means that this is equal to dui, all of it, by dx plus dvj, all of it, by dx plus dwk by dx. Now this is important because in cylindrical coordinates, you're going to have er and e theta and ez, and the derivative of er or e theta with respect to theta or with respect to r is not equal to 0 or is not equal to 0. So you cannot take out the unit vector out of the derivative. For Cartesian coordinates, for Cartesian coordinates, what you do here, this is u di by dx plus I du by dx, but di by dx is 0, so you essentially can pull I out of the derivative, the unit vector. But for cylindrical coordinates, that's not the case. So I'll give you the formulas in the assignment, what the derivative of ER with respect to theta is, and what the derivative of E theta with respect to R is, etc. Remember, in cylindrical coordinates, as theta changes, so does ER, right? It doesn't point in the same direction anymore. But for Cartesian, those derivatives are 0. And so then you can say dv by dx j plus dw by dx k. Okay? And you take this, plug it back in here. Same thing for du vector by dy, same thing for du vector by dz. You collect terms in the I direction, terms in the y direction, and terms in the z direction, and that gives you all the three components. So same thing here, du vector by dy is du by dy I plus du by dx, sorry, du by dy I plus dv by dy j plus dw by dy k, and same thing for du by dz vector is equal du by dzi plus dv by dzj plus dw by dzk. Okay, when you combine all of those, you're going to get, for the in the I direction, you're going to get u du by dx plus v du by dy plus w du by dz. Those are the I components. The j components, you get u dv by dx plus v dv by dy plus w dv by dz. Okay, and so on. Yes. Here? Yeah. Because this is the gradient of a vector.
Yeah, but we know that the vector is uw and uv.
No, but this is gradient of a vector. The gradient is going to apply. So each component of the gradient applies to the vector. So this is like saying, so grad u is not equal to du by dx, du by dy, or dv by dy, dw by dz. That's not equal. No. This is a tensor operation. This is gradient. So if you remember, this is a dyadic. So if this is another way of doing the dyadic. This one is simply d by dx, d by dy, d by dz into uvw. It's a 3 by 3 matrix, right? But this is a nicer way of doing all of this, okay? So keep that in mind. All right. Today we are going to derive the Bernoulli equation. Who's heard of the Bernoulli equation? Famous Bernoulli equation. You've all done Bernoulli. Do you know how to derive it? So Daniel Bernoulli, one of the great Bernoulli brothers, was the one behind this famous equation. He used energy arguments to do that derivation. At the time, they didn't have differential calculus and all of these fancy equations, okay? But we do, right? And we're going to follow the mathematical argument to derive the Bernoulli equation because it's going to give us the most general form of the Bernoulli equation, okay? And we'll see where it applies, why, and what are the limitations, all right? So we're going to start with our weak form of the Euler equations. So remember, mass conservation, we covered it, we got it. We know for mass conservation, we have d rho by dt plus div rho u equals 0. We got that equation done. Now for inviscid flows, we derived last time du by dt plus u dot grad u equal minus grad p plus minus 1 over rho grad p plus g vector. So what can we do with this equation? Our objective is to find u and p, right? Or we might know p, then our objective is to find u, but this is a very difficult equation to solve analytically. Okay, so there are ways to do it. What Bernoulli essentially did, well, Euler actually showed how the Leonhard Euler, that's his name, Swiss mathematician, one of the greatest mathematicians in all time, even greater than Gauss, in my opinion, but that's my opinion. So he took this equation and integrated it. We're going to follow his methodology. On my blog, I have an entire series of how Euler derived the fluid mechanics equations. It's really beautiful. You should see how he did mass conservation. He took a triangle and kind of moved it around in a flow and did the derivation. Anyway, okay, so what are we going to do? We're going to consider a fluid flow, right? It's got kind of things like that in it, etc. Okay, you got Vortical structures maybe. And then Euler said, well, if I want to integrate this in time, it doesn't help me, because when I do an integral in time, I just get this derivative disappears, because this becomes integral of a derivative with respect to time is just the integrand. So it will be u at n plus 1 minus u at t0. So it doesn't, so this gets knocked out, but we can't do anything with these things. So instead he said, you know what, I'm going to integrate this equation along some path, some curve C, okay, from point 1 to point 2, okay, along this curve, this red curve. And you can write then integral from point 1 to point 2, those are arbitrary points, okay? du by dt dc, okay, that's the integral along that curve. What is dc? Is a differential element on that curve, and it's actually described by a unit vector that is tangent to that curve at all times, okay? That's what dc is. It's like the integral to calculate the work done by a force. So you get plus integral from 1 to 2 of u dot grad u dc equal integral minus 1 over rho grad p from 1 to 2, also dc, okay, plus integral from 1 to 2 of g dot dc. I'm going to add a dot product over here just to kind of make this more rigorous. Okay. Now, why did Euler do that? Because in anticipation of getting rid of integrating this equation, he noticed that, well, there's a gradient over here. We'll do something about 1 over rho. There's a gradient over here. We're going to do something about u dot. This one can be expressed as a gradient. And as Euler, I know all the math in the world. So I remember that the integral along a curve from point 1 to point 2 of grad phi dc is equal phi 2 minus phi 1. So in other words, the work done by a potential, if you remember your physics, potential energy, right? It's the work done by a potential. A potential is described by the gradient of a scalar. The work done by a potential along a curve is simply the work at the end minus the force at the end minus the force at the beginning, right? That's what matters. It doesn't matter what path you take for a potential type energy. So for example, you're taking a bucket of water, you're taking it from, you know, Salt Lake Valley all the way up to President's Circle. It doesn't matter what path you take, the energy stored in that bucket of water once you get up there is going to be the same. It's going to matter, what matters only is the difference from sea level to the top. Okay, that's what this is saying. So Euler thought, look, if I do this integral and if I can convert each one of those to a gradient, then I can essentially solve this equation. Okay? Okay, let's do that. So we got a u over here. Okay. Now, for this integral, we can't really do anything because it's just simply cannot be expressed as a gradient. Okay, so what we're going to do, we're going to assume that this is, if we want to knock out this integral, we assume a steady state flow. There's a way to keep it and you get an unsteady Bernoulli equation. We'll talk about that later. But you can, if you assume steady state, then this integral goes to 0. Okay, we got rid of this first integral. Okay? All right. What about this integral? Integral of minus 1 over rho grad p dc from point 1 to point 2. Only if we could get 1 over rho outside of the integral, then we would have just a gradient, right? Why do we have 1 over rho inside the integral? Because in general, rho could be changing inside the flow field along a streamline, or along a curve. Forget streamline. We haven't said streamline yet, so scratch that. So rho could be changing along this red curve in general. But if we assume, and it's a reasonable assumption, we could say we're just dealing with constant density flows, then that takes away that entire issue, okay? Assume rho is equal to a constant along curve C, just along C. So if you choose C in a way such that the density is constant along it, then you're good. You could have another curve here, C2, and it could have a different density than C1, but as long as the density is constant along it, then you're good to go. So this one could have rho 1, this one could have rho 2 on it. It's okay. Okay? So then we can take out 1 over rho out of the integral, correct? Because it's not a function of C anymore. It's not a function of the position along C. So then you could say this becomes minus 1 over rho integral from 1 to 2 of grad P dot dc. And we can simply apply this formula. You get minus 1 over rho P2 minus P1. Good. We knocked out one integral. Okay, let's look at this one. Integral of G dot dc. So you've heard in your physics classes that gravity is a potential force. Okay, the action of gravity is a potential result of a potential. So we're going to use that to our advantage now. Math has a lot of power if you know what you need to do. A great way to think as a graduate student is to reverse engineer the problem, just like we're doing right now. Our objective is to integrate this equation, and to do it, we want to convert everything to a gradient. So that's what we're looking for. We're finding ways, all sorts of ideas and theorems and assumptions to convert these all to a gradient form so that we can integrate them. We're kind of reverse engineering the problem. So let's look at this guy. Okay, integral from 1 to 2 of G dot dc. Okay. So now consider, for simplicity, consider a Cartesian coordinate system. Cartesian coordinate system, X, Y, Z. Okay. Then at any point R, could be x1, y1, z1, etc. If G has the following components, gx, gy, gz, then I want you to evaluate the following formula. What is this equal to? Right, take a moment. And show me what this is equal to. So in other words, the action I want you to evaluate if at any point R, so this is point R, X, Y, z. And then there's a gravitational force, gravitational acceleration g, gx, gy, gz. I want you to evaluate grad of g dot r. So first evaluate g dot r, and then take its gradient. And grad, remember, grad is d by dx, d by dy, d by dz. So first calculate g dot r. R is x, y, z, and g is gx, gy, gz. Do the dot product. Then take the gradient. You don't need parentheses when you write it this way. Okay, so do it. Do the, yeah, one more step. Now assume that gx, gy, and gz are constants, okay? Assume that gx and gy and gz are constants. That's implicitly assumed. So each one of those is a constant. Okay, you got an answer? Ellie is almost there. Hafiz? You're almost there, Nick. Just one more step. What is the, Nick? What is the derivative of dax by dx? A. What is the derivative of gx times x by dx? Okay. Be careful. Is this a vector or a summation? Okay. So what's the answer? G. Yes. Okay, so let's do it. So Louise is saying that G is simply gradient of G dot R. So thinking ahead, my objective is to express G as a gradient of something. That's my goal, right? It turns out that G is the gradient of G dot, the position vector. So how do you show this? G dot R is Gx, Gy, Gz times X, Y, Z. So that's equal X, Gx plus Y, Gy plus Z, Gz. Gradient of this is equal d by dx of all of this, okay? Because that's the gradient of a scalar. I plus d by dy of all of this quantity, okay? J plus d by dz of this entire quantity, k. Well, d by dx of this entire quantity is simply gx I plus d by dy of this entire quantity is this guy, gy, j plus d by dz of this entire quantity is gz k, which is equal to g. Some of you had some mistakes here. You should, when you're taking the gradient, you take the gradient of the entire scalar, not just the x, y, or z component. You will lose points for this because that's a theoretical error. Okay? So you're differentiating the entire quantity. It just so happens that these guys just disappear. This is great because now what we can do is say the integral from 1 to 2 of g dot dc is equal the integral from 1 to 2 of the gradient of g dot the position vector dot dc. Okay? And that's equal to g dot r1 minus g dot r2 minus g dot r1. Isn't that cool? What is r1 and r2? They're the position vectors of point 1 and point 2. Thinking ahead, if you know the Bernoulli equation, that's the z term, gz, correct? If gravity only acts in the z direction, then the only component that matters is going to be z2 minus z1. Okay? gz2 and gz1. Okay. So we agree now. We pretty much are left with this annoying term. We haven't said anything about the curve C. The only thing we said is that the density needs to be constant along that curve. So it might be that we can pick any 2 points in a flow. Unfortunately, that's not going to be the case because what the assumption we're going to make here is going to force us to choose the curve C in a more restrictive way. Okay, may I erase here? Who's kind of starting to give up? I hope not. Look, many of these things, I don't expect you to know, like, because we're learning these things, the vector identities and all of those things. You're being exposed to these things, okay? There are some things that I expect you to know, right? But then we covered the vector calculus and, you know, we're learning about these things together, okay? When I learned this stuff, I was like, wow, this is so powerful. The ability to negotiate with the equation is so reliable, you know, as compared to intuition, because intuition is going to rely on observation. Without seeing the observations for inviscid flow, you're not going to be able to make those intuitive jumps to derive an equation. But the math is always reliable, okay? All right, so we still have the integral from 1 to 2 of u dot grad u dot dc. Okay, well, our objective is to convert this guy into a gradient, okay? There is, thankfully, a vector identity that says u dot grad u is equal. You can find this on the list of vector identities on Google. It tells you that this is the gradient of the kinetic energy. Good. We were now able to extract a gradient from this guy. Minus something. Minus u cross omega. Okay, unfortunately. So this is a gradient, that's good. We can put it in the equation and integrate it. But this term is u cross omega, which is the vorticity, which is curl u. So it's this term is the cross product of u and the vorticity, okay? Okay, so that means our integral is integral from 1 to 2 of grad u squared over 2 dot dc minus integral from 1 to 2 of u cross omega dot dc. This one is easily integrated. It's u2 squared over 2 minus u1 squared over 2. You remember this from your Bernoulli. Comes from this term. But this guy, what are we going to do with this guy? Let's make, I want to hear some assumptions.
Assume that the flow is irrotational.
Okay, very good, Ali. Okay, so Ali is saying, assume flow is irrotational. So what does that give us, Ali? What does that mean mathematically? Omega is 0. And therefore, Ali wants to get rid of this term. I agree with her. I want to get rid of this term. I know that there's no way we can express this term as a gradient. Okay? There's no way we can express this term as a gradient. So the only way we could get rid of it is to get rid of it. But under what conditions? Ali is saying if omega is equal to 0, therefore the flow is irrotational, then this implies that u cross omega is equal to 0, and we don't have that integral anymore. Correct. And you'll get the answer. But irrotational flow is very restrictive. So like last time I asked you, give me an example of inviscid flow. Now give me an example of an irrotational flow. Pretty much non-existent. Okay, unfortunately. So while the irrotational flow assumption is valid, and it does give us actually the Bernoulli equation. So when we plug in these terms with irrotational flow, the result is going to be, what is it? Write it down. So we get u2 squared over 2 minus u1 squared over 2 equal to minus p2 minus p1 over rho, correct? And what about the gravity? Plus g dot r2 minus g dot r1. So we're able to integrate the equation. We know g. If you know your pressures, you can calculate your velocities. And that is indeed the Bernoulli equation, but it's very restrictive because this is saying this is only valid when the flow is irrotational.
So what if the velocity is in the same direction of the vorticity, and that product would be 0 too?
Okay, so that's okay. But what does that mean? So Ali is taking over the answers today. Okay, so Ali is saying another option would be if you, so when is a cross product equal to 0? When is a cross? When they are parallel. So that's why we remember when we learned those lessons early on, when they are parallel. When u is parallel to omega. But is u ever parallel to omega? Why not?
Because it is a cross product.
Yeah, because it's always perpendicular to omega.
But we can do u cross w perpendicular to these.
Yes. Okay. I love it. All right. So let's rewind. Okay. So for the first way we could eliminate this guy is simply assume omega is equal to 0. And that checks. Second one is to assume u cross omega is equal to 0, which implies that u is parallel to omega. But that can never happen because by definition, omega is equal curl u. And that means that omega is perpendicular to u. Agreed? The cross product, right, creates a perpendicular vector. Because omega is curl u, then omega must be perpendicular to u. So if this is u, this would be omega. Okay? Now Luis jumped in. Pardon me? Did anyone say anything? Just the voice in my head. It happens every now and then. Okay. Now Luis said, well, look at u. What if we took u cross omega, that entire vector, dot dc? What if we look for vectors for conditions when C, what if we choose C such that DC, the tangent to C, is perpendicular to the vector U cross omega? So you agree that U cross omega creates a vector. Okay. What if we choose C in a way that is perpendicular to U cross omega? So can you help me figure that out? Oh, sorry. Yes. C is parallel to U. Why? What would that mean? So if C, I want to build on that. So if DC is this way, right, and U is also this way, then so U cross omega, it must be perpendicular to C because it must be perpendicular to U. Agreed? So U cross omega is always perpendicular to U and omega. That's by definition of the cross product. U cross omega is a vector B, call it B, that's always perpendicular to U and omega. So therefore, this guy is perpendicular to U. Then if we choose C to be parallel to U, then their dot product is going to be 0. So what is a curve C that is always parallel to U? It's what we call a streamline. Fluid mechanics, a streamline, it's what you draw. When I ask you, draw the flow, right now, draw the flow over a cylinder. Just draw it for me. Draw the flow over a cylinder. Yeah, what are you drawing, Nick?
I drew a cylinder from the side and
Yeah.
the flow going around.
Yeah, what are these lines? They just, the streamlines. They're the velocity, put now the velocity on each one of those lines, right? Right, so put like little arrows. Right, it's tangent to the streamline. So C, if we choose C, if we choose C to be identical to a streamline, then we satisfy, then U is parallel to DC. And the streamline is the intuitive, this is what you draw, right? Flow over a cylinder, that's what you draw. What are you drawing? You're drawing the streamlines. The velocity moves along the streamline. You don't need any fancy definition of the streamline. Good work, you guys. Love it. Yeah, you're using all these little tools that we have. So choosing a streamline is less restrictive than going with potential flow, right? Because a streamline exists in all realistic flows. Okay, so you don't have to be irrotational. All you have to do is choose C such that it is a streamline. And if it is a streamline, then this guy goes to 0. Okay, so now we have all the ingredients that we need to get this equation, to fulfill this equation. So this guy we said is equal to grad U squared over 2 minus U cross omega, integral. Okay, let me clean it up a little bit. Integral from 1 to 2 of grad U squared over 2 dot dc minus integral of U cross omega dot dc from 1 to 2. This is equal to 0 if and only if C is identical to a streamline. And therefore, the answer is the Bernoulli equation. You get U2 squared over 2 minus U1 squared over 2 is equal to minus P minus P2 minus P1 over rho, correct? Plus G dot R2 minus G dot R1. Okay, let's build on that equation a little bit. Are we done here? I hope. So I'm going to separate the terms, the values at point 1 from the values at point 2. Okay, so we have a minus U1 squared plus P1 over rho plus G dot R1, right? Make sure I got it right. Okay. So there's one more thing we can do before I write it here. So if we live on Earth and G is equal to 0, 0 minus GZ, or just minus GZ, right? So what matters here is, so this becomes minus P2 over rho plus P1 over rho plus G dot R2, so dot R2, which is X2, Y2, Z2. Then this becomes minus GZ, Z2, so minus GZ2 plus GZ1. Agreed? It's just simply the height between these 2 points. So if this is Z2 and this is Z1, whatever reference you're at, sea level, okay, that's what matters. So now we can write the Bernoulli equation. With the signs we got a minus U1 squared minus P1 squared over rho minus GZ1. Multiply everything with by a negative sign, you get U1 squared over 2 plus P1 over rho plus GZ1 is equal to U2 squared over rho plus U2 squared over 2 plus P2 over rho plus GZ2. What are the assumptions, the conditions under which this equation is valid? Rho is constant along a streamline, and points 1 and 2 lie on a streamline. And the flow is inviscid. Correct? So the Bernoulli equation is simply a solution to the Euler equations along a streamline. So in other words, if you take the Euler equations and dot them with a streamline unit tangential vector, you're going to get this answer. Okay? And that's the Bernoulli equation you're familiar with, right? See how cool this is, how we derived it from this nasty complex partial differential equation we got here. Now, Bernoulli got to it from energy arguments. He said kinetic energy plus potential energy plus some energy related to the pressure work should be constant along a streamline. That's what he said. Because making this statement, U1 plus P1 plus GZ1 equal U2, P2, etc., what this necessarily means is that the following quantity, U squared over 2 plus P over rho plus GZ, is equal to a constant along a streamline. So now the big question, when can you apply the Bernoulli equation and where? Okay. First things you want to sort out is that you should be able to make the assumption that the flow is inviscid. Usually, if you're dealing with like air, you know, it's got a low viscosity, you could say, oh, it's fairly inviscid, or what we discussed about last time. That's a fairly easy assumption to say. You can assume density is constant, okay? But the challenge is finding situations where you have a streamline. So let's look at a few examples. We're going to do more examples next Monday, but let's just kind of think about this through. You have an airplane. Take like a little fixed wing air jet or whatever, okay? You got flow around it, right? You got crazy things going on here. And then you have, away from it, you have things like this, nice things like this. So you can apply Bernoulli over here. Okay, Bernoulli. But not over here, right? Because over here, the streamlines are breaking, they're detaching, there's all sorts of energy transfer and changes going on, okay? My fireplace at home. Okay, so you got the chimney, you got some fire going on. And what happens in the fireplace, you get air, gets sucked in and usually goes up, right? Now, although this is a streamline, it might, kind of have some little change in structure, but still a streamline. You can follow it, okay? But something crazy is going on here. You're adding energy. So I wouldn't apply the Bernoulli from here to here. I would instead apply it from here to here and maybe from here to there, okay? And these constants will be different. This might have a constant C1. This might have another constant C2, okay? It's different because you added energy to the system. There's a way to incorporate this sort of stuff into the Bernoulli equation. We're not going to do that here, but there's a way to compensate for those changes. If you have like flow over, you got a fan, okay? Don't apply Bernoulli across the fan because you're adding energy or you're subtracting energy. So apply it from here to here, from here to there. Your Bernoulli equation is your back of the envelope calculation. You're with your kid and like Mark always, my son's name, he always asks me like weird questions. Like I would expect him in a year or so to ask me, Daddy, what is the velocity of the flow at the bottom of this tank? And we're like, at the top of Mount Everest or something. I'm like, so I gotta grab a little notepad and do the Bernoulli equation, okay? Give him an answer. He's been very obsessed with Jupiter lately. Unfortunately, my telescope is broken now, but he looks at the giant red eye and he calls it, it's called a raging storm, Daddy. And so, we can't apply the Bernoulli equation inside that raging storm, okay? So what did you think? The way we derive the Bernoulli equation? It's really cool stuff. Cool math. There is power in math. Gives you an edge, okay? And what you guys did today, the way you critically thought about U cross omega, I love it. Okay, I'm gonna add more math. But good thinking. This is great. Okay, so I'm thinking next week or the week after, we might take a break from all this math hazing and potentially watch like a little fluid mechanics video together. I'll try to bring pizza or something. We can do it in a different classroom. Okay, if that works, we can take a break, watch some experiments, etc. Okay, and yeah, chit chat about it a little bit. All right, thank you so much. You have a nice weekend.
Can you let me know what day we'll do that so I can bring my own food?
Oh, okay. Yes. Okay. So I could get no cheese, I guess.
I have a celiac.
Okay. Thanks for letting me know. We'll get you something. I will ask if there are some dietary restrictions. So Hayden will pay for it.
Clear about this.